Greetings, everyone. Thanks for joining us for today's Performance IQ webinar, which is the second in our series covering network performance and gamer experience across key global markets. I'm Michael Baylor, I'm the CMO of GameBench, and I'll be hosting today's webinar. In our last session in June, we dug into the UK market. Today, we move to the massive and, of course, fast-moving US market, going coast to coast to look at leading ISPs Cox and Optimum, unpacking all the key metrics, and explaining the GameBench techniques and technologies that deliver them. For anyone who's new to us, I'll give the briefest possible intro to get us into the chat as soon as possible. If you want more background, and also if you'd like to check out our insights and our learning materials, which may be valuable, particularly if you're new to the space, do check our website, which is at gamebench.net. So, for 10 years, GameBench has been a pioneer and world leader in game performance management. We serve two complementary markets. On one hand, we provide performance analysis, benchmarking and monitoring services worldwide to ISPs, mobile operators, and device manufacturers. And on the other, we deliver performance testing and monitoring software and services to leading game developers and publishers. As you can see from the chart, which I think is on the screen now, the GameBench approach has won us market-leading clients across the entire ecosystem, which makes us very happy. So that's the corporate bit over and done with. My good colleagues, Karthik Harikrishnan, who's the GameBench co-founder and CTO, and Michael Efthimiou, our senior technical consultant for the US, will be running today's discussion. Before I hand over to them, just a couple of points about how we're running today's session. Hopefully you'll have plenty of questions, and we'll be responding to them as we go along. So we don't save them up until the end. We do them periodically at breaks during the conversation, which we find actually works much better for us. Put them into the chat as soon as you like, and we'll aim to bring you live into the discussion to go through them with the panel. So in other words, be ready to become an instant panelist with us. Can I also, just as based on a couple of previous experiences, can I also please ask that we stick closely to the topic in hand? I have to say that any inappropriate comments or questions will not be picked up in the chat or the live discussion. This is not to punish anybody, just to make sure we have a good quality experience for everyone who's here. We will be wrapping promptly on the hour, and if by any chance you don't get a chance to discuss your questions with us here, we will try to follow up with you. We do keep track of all questions, and or of course, please do contact us after the close. As always, we'd love to hear from you. Right, that's quite enough from me. Kay, over to you.
Thanks, Michael. Thanks for the introduction. Hopefully you guys can hear me all okay. So the first part of this webinar, I'm going to be talking about game performance metrics. What are the metrics that matter, and how do we measure them? What are the techniques we use to measure them? And the second part, what do those metrics actually mean when it comes to after we measure it, and then what is the sample data that my colleague Michael will be able to take you over. So let's start without wasting any more time. So what we're going to be focused on here when we say gaming metrics is for network-centric gaming. Now, we've coined the term network-centric gaming to capture two aspects of gaming. One is native gaming, and the other is cloud gaming. When we say native gaming, what we effectively mean is that the rendering happens locally. You have a big, powerful PC where you spend thousands of dollars getting a good GPU, and then obviously you're rendering the game on the GPU, whereas in the cloud, the rendering happens in the cloud. The metrics that matter are, even though network dependent, they're slightly different. In the case of your native gaming, it's your round trip time that to the gaming server that matters. You're also looking at packet loss jitter. Your local frame rate typically is dependent on what spec of what PC you have and how spec it is. Your experience also depends on what the server tick rate is. So this is something we'll go into in the next slide. When it comes to cloud gaming, which will be the focus of this particular webinar, the key metrics that we're going to focus on are end-to-end latency, or what gamers call as input lag. Then you're also, when it comes to quality of experience, the encoded video frame rate and the encoded video resolution also play quite a huge part. Moving on. Just a quick understanding of what factors might affect your online gaming experience. So here, there's a few different issues. Obviously, one of them is got to do with what's called a slow motion servers. So this is when, as you know, when you play a native game, all your inputs and events are sent across from your client across to the game server, and the game server runs simulations to understand where every person or every character should be placed. What is the current state of your world? All of that will be crunched on the server side, and then that will be broadcast back back to the client for it to render. So this is, how many times this happens is called the server tick rate. For instance, if you were to go, play a game like Apex, your server tick rate is 20. If you play Valorant, it's 128, CSGO 64. So basically it means CSGO 64 times in a second, you update the physics, and that's the number of simulations it carries out. Now, the lower the tick rate, you would see the game might feel less responsive. So that's an area where, but game to game it matters. The other areas are, you would obviously have a lot of times, we've seen that 80% of issues are, happen because of poor Wi-Fi, where you could, simply by changing channel, moving closer to the router, using 5 gigahertz, standard things like that, you'd be able to actually improve your gaming experience. Some aspects that are actually out of your control are what's called routing or peering. In the simplest possible term, if you want to explain peering, it's basically how two networks talk to each other, right? Sometimes when you want to send a packet from one side of the world to another side, you could follow a route. There's always a route that a packet can take, but typically big gaming companies or big operators and ISPs have arrangements between disparate networks where they can actually route that traffic in a more efficient manner. So sometimes there might be, when you're sitting in one location and you're trying to connect to a server, you might have poor routing, or places where your ISP or your mobile operator doesn't have the right peering arrangements with different networks. So these are broadly the kind of topics that can affect your native gaming experience. Moving on to cloud gaming, what is it that matters? As I said, one of the key things that matters in cloud gaming, given all the rendering happens in the cloud, is input latency, and this is something that affects responsiveness, how responsive the game feels. So when we say cloud, when we say input latency, what we mean is, as a company, we try and look at what the end user sees. So we don't look at proxies, we don't look at the ping to the game server, or how much does a UDP packet take to go to the game server and back. What you want to actually measure is what the gamer feels, and that is what's the time between a mouse when you left click a mouse button. In this case, in this particular screenshot, you can see when you left click your mouse button, you can actually see the gun flash happening. So you want to understand what's the time between left click where your mouse button pressed to the first frame where you get the gun flash. Then the second aspect is when it comes to the frame rate, there are two aspects of frame rate. One is obviously the encoded frame rate. What is the server encoding? What is the frame rate encoded by the server? And what is the observed frame rate? Sometimes a lot of the times, in case your decoder is not able to cope, or because the client is not powerful enough to decode the frames that that have been sent by the server, those two might be different. Ideally, you want to, you'd hope that the encoded frame rate and the observed frame rate are the same, but you want to be looking at measuring what's observed by the end user. Video resolution is again a tricky one that impacts the user experience a lot. You've got different platforms. So in this case, for cloud gaming, you've got different platforms adopt different strategies when it comes to video resolution. Some platforms will prioritize frame rate over resolution and try to keep a standard 60 FPS frame stream going, whereas other platforms will want to keep a standard resolution and modulate the frame rate depending on the network conditions. It also depends on things like Wi-Fi and 5G. If you're using Wi-Fi, typically operators tend to give you a better stream, whereas on 4G or 5G, we've seen that the maximum streaming resolution is generally limited to 720p. So now those are the metrics that matter, and what, as a user, if you care about cloud gaming performance and you want to measure them, those are the three metrics that you want to capture to quickly understand a gaming experience. Now let's move into the techniques itself. How do we actually measure these things? So on the right-hand side here, the first topic that I would like to cover is input latency. So in this case, there is the classical way by which you can measure that. On the right-hand side, you can see is, we've gotten a mouse, which we've instrumented. When we say instrumented, the left button click is actually connected to an LED, as you can see here. So every time I press the left mouse button, the left the LED will light up. And then obviously when you're using a high-speed camera, you can actually take a footage of the whole thing. So in this case, the equipment or the laptop in this case is actually kept inside a black box, and you're actually taking a video of the whole thing. And when you take a video of the whole thing, you'd be able to manually count what's the time difference between when my LED lights up to when the first first frame. There you can see there was one of the frames. I'm not sure if in the video conference it's obvious, but you can measure the difference between the LED lighting up to when the first frame holding the gun flash comes up, right? So it's a very manual process, but it works. And this is what we would call as the golden reference for measuring something like input latency. Then there are a couple of, NVIDIA has a useful piece of kit called the NVIDIA Reflex Monitor, through which, if you have a compatible mouse, you'd be able to measure the input latency by drawing a region of interest, which is in the form of a rectangle. You'd be able to move that around, and then the mouse is a pass-through mouse. What happens is the input events get captured by the monitor, and then it's able to work out when there's substantial difference in a region of interest. And then we also have our own solution, which is called ProNet Windows, which we think of the world's the first software solution that can instantly measure, none of the faff of hardware, instrumenting mouses and high-speed cameras. It'll instantly measure and report what game input lag is without using any external hardware. The advantage of using a purely software solution is that you can get your time savings are enormous. In this case, we've measured that it could be up to 200x compared to using a high-speed camera. Moving on, the next aspect, frame rate. So we covered input latency. Now going on to frame rate, there's again multitude of things that you could use, especially when it comes to Windows, to be able to measure what is my frame rate, what is the experience I'm getting. So the first thing is you again rely on a high-speed camera. It is again very cumbersome to use, but it clearly does the job. You could also rely on on-screen displays. Many of the games actually come with displays where it will tell you on what is the frame rate I'm seeing. For instance, on the screenshot up above here, this is a screen. I think it's one of the platform providers. They can actually list you a bunch of interesting topics, including frame rate on the screen. The other thing is WebRTC. WebRTC is quite a useful piece of kit, especially if using Windows. You could go into in the Chrome browser, be able to go into Chrome WebRTC internals. You'd be able to understand a number of this. The screenshot down here you can see is a screenshot from WebRTC live graph. So it actually tells you what the frame width is, frame height is. A lot of the cloud streaming platforms, including GeForce Now, Stadia, and xCloud, when they have a browser-based implementation, use WebRTC, and you'd be able to understand some of the key statistics that they're streaming at. And then you can also use native Windows tooling like PresentMon. You use vendor tools. So there's an assortment of tooling you can use to be able to measure frame rate. We also support as GameBench. We also support as part of the software tooling, you'd be able to measure what frame rate is actually seen by the user. The next part is resolution. This is probably the trickiest metric to actually objectively measure. There is, you'd have to, a lot of times, the reason I say that is because you could have a 720p video, but 720p can be encoded in different quality, different quality formats, right? So you could have a very high quality 720p and a very low quality 1080p stream, both looking the same. So it's very hard. We've done a lot of experiments to see if this can be extrapolated from just a screenshot. It is very hard. So you would have to generally rely on like the WebRTC stats that I showed you earlier. That's a good place where you can actually go and find out what the resolution is. Or you use logs. In a lot of cases, there are logs by like for instance, NVIDIA GeForce Now will log what resolution is being sent in the system logs, or to use things like WebRTC. So, or in this case, you can actually turn on an overlay. This is an Android. I can't remember which platform it is. You can actually turn on and understand what the resolution is. Now you might have another question, which is pertinent not to native gaming, it's more pertinent to cloud stream gaming. Image quality is important, right? How do you capture, how do you measure blockiness, right? If I'm being streamed a video, obviously you want the video to be less blocky as possible. So this is something that's again quite a interesting area. So we have an algorithm that uses blockiness, computes blockiness in every frame, and then it gives you a score. So in this case, you can see if you have a bad connection, you can see that the blockiness increases as opposed to the blockiness metric in a good connection. Another, this is one of the approaches, but we would like to. Probably the most advanced piece of literature I've seen when it comes to video quality is what Stadia have done, where they've used a machine learning based MOS prediction kind of algorithm, where they trained a lot of users to give them MOS scores, and then they have an ML based algorithm to actually predict what the MOS score is for any particular video. So just to give you a feel of what does it mean to compute, how does this software solution work? Just thought I'll give you a quick understanding, give you guys a quick run through of how this is implemented in our tool to understand how it's measured. So in this case, the scenario is this. So this is Gamebench ProNet Windows tooling, where the aim of the tool is to measure input latency of fortnight. So in this case, there's two monitors set up. The tool is running in one of the monitors, and a game is being played in the other monitor. So here you can see the first thing we select is we go and select what the game is. After that, we go and select what display I want to profile it. You want to select which display is running the game. After that, you select what is the region of interest. So, the reason we need the region of interest is because, as I mentioned earlier on, if you want to measure input latency, we need to look for some change. And what we are interested in is looking for a flash near the gun muzzle. So we tell the software where, what is the region where we are expecting significant change when it comes to luminosity of pixels. So there's two things that you need for input latency. One is a trigger. What is the input trigger? So we tell it it's a mouse. It's a left mouse button. So the software will register any buttons, any left mouse buttons that are being pressed. There are other options too. We can connect an Xbox controller, for instance, and look at the A button or the Y button or the trigger, left trigger, or left bumper, so on and so forth. But for this example in this video, we had the left mouse button pressed, and then the software will detect if there is a luminosity change. So here you can see a couple of sliders over here, but essentially what those sliders do is to tell the software what is it that we need to detect as a change. So once this is configured, you can simply play the game, and then the software will measure latency as on the fly. And once it measures, all the data gets, you can stop the recording, and all the data gets uploaded to a web dashboard, which you'll soon see. Once this person finishes shooting, you end the session, and you stop the session, and all the data gets uploaded centrally to our web dashboard. You can also, there's a feature by which you can tag different experience. For instance, you could actually tag what the user experience was, what the game was, if you're playing a cloud stream game. So in this case, it was Fortnite, where you're actually testing, what device did you test on, what platform did you use, and all this data gets uploaded to a Gamebench web dashboard. This is all useful because this is exactly the sequence we use to collect all the data that Michael will be talking on later on for the US ISPs. Then there is ways by which we can download the data. We can export all of this, all of the data that was collected is readily available for post-processing. So I'll move on in the interest of time. We've also, we understand that from a lot of our clients, we understand that this is something that a manual, it's still manual, but, so what we've been doing as part of the labs here is to actually automate the whole thing. So we've got what you've seen there, but, completely automated. So here you can see it's a robot, it's a bot actually going and clicking through GeForce Now, and then it will play Destiny 2. It will navigate through the menus. At some point, you will see that I'm just fast forwarding. Where it will actually get into the game. It will fire a few rounds, and when it's doing all of this, the software in the background is measuring a bunch of performance parameters, including input latency. It measures input latency, frame rate. So here you can see it landed into the game level. And once it lands into the game level, it's actually performing automated runs. So by this, the team's actually able to collect thousands of samples. Instead, if you were to actually collect the sort of samples manually using a high-speed camera, it's almost impossible to collect even 100 samples. So yeah, so this helps us to collect real user metrics, real input latency, real frame rate that the actual gamer is saying. We don't guess. We leave nothing to guess. Where we actually measure what the user is saying, and then when we are actually trying to benchmark a service.
Couple of questions, Kay.
Yeah.
Before you're going to hand over to Michael, I just thought there's a couple of questions that might be a good time to bring them in.
Go ahead.
That relate to your presentation. Here's a very brief one. Can we test any game?
Yeah, there is one. I would say yes with a disclaimer. So as you can see, the software is based on region of interest around a particular. So that region of interest ideally should stay the same. So in the case of games like Fortnite and Destiny 2, which are quite popular games, it stays the same. And we can use in certain areas, you can go and profile, but that gives a good indication of how the overall service is performing. We are also investing in being able to detect the changes using machine learning, where we're going to classify if a particular frame holds a gunshot or an action. For instance, if you use racing games, you would look at brake lights, for instance, or if you were to use, first-person shooters work really well, but in other games, we have seen other kind of actions that are suitable for this. So yes and no, we've started with 2-3 games, but we are going to expand it to use machine learning to incorporate other, where the camera changes and focus changes.
And actually, that links very nicely to another question we have here. And this is very much more specifically from a QA point of view. Obviously, in the QA community, we are known, GameBench is known to be very much focused. It's kind of a USP for us on real gamer experience. Towards the end of your presentation, we saw the shift in ProNet from the manual option to more towards the automated option. From the QA point of view, as we move from manual to automation, is there anything from the QA quality, from the QA data point of view that we're losing in that transition, do you think?
Well, not from a performance standpoint. I mean, obviously, from a functional standpoint, you would be losing. For a performance standpoint, we've seen that in a cloud game, you could easily profile. Once you get into the game, you get a lot of feedback, even if you're not playing the game. For instance, we'll be the first person to accept we're not actually. We are getting into the game, and we are, we are in Cosmodrome, as we saw, and then we are spinning around in a level in a game, and we are collecting measurements. But this is good enough to understand if the network has a huge impact on the game. So from a performance standpoint, you're not losing much, but when it comes to a functional standpoint, obviously manual testing is needed, because you have to go through, let's say you're testing the game, you have to go through different levels, see if different characters are behaving as they should, different levels. Once you finish a level, are you getting to the next level? All of that You could automate all of that as well. And we know we have partners who help in automation of all of that. But in the absence of that, you can't take away manual testing. So manual testing still has its place, but we feel if you want to get reliable data to be able to compare on a daily basis, automation plays a huge part.
Really clear. Thanks so much, Kay. That's great. We are now gonna move on to Michael, who's going to take us through some of the more specific details on the metrical outputs that we have from the work we did with Cox and Optimum. Michael, over to you.
Thank you, Michael. So let's jump in then. So first metric we're going to talk about is input latency. Karthik's covered this in some detail. So just to remind everyone, the input latency metric effectively measures the responsiveness of a user input. And we calculate the user perceived latency by measuring when an input is initiated to the first frame of corresponding action seen on the screen. So this reflects accurately what responsiveness an end user or a gamer would experience when playing the game. So we collect metrics for each shot or each jump, whatever we're triggering off for our latency metric. So we collect one sample, and for each of those samples, we'll aggregate them, create some statistical, metrics. Now, metrics are great. Averages, aggregations, are useful, but they can mask some of the session-specific issues we might see in the game. So what we do is we bin each sample into one of our ratings that we've listed basically here. So we have poor to ultra as far as our input latency rating, and then for each of those we have some thresholds that we look and we group the input latencies into. So the reason we do this is that this gives you a better idea of what the user experience would be over one session or aggregated number of sessions for that particular device or that network. And it's a much truer sense of what the user would experience rather than just giving one grade as an average of good or great and then missing some of the poor samples or poor experience during those sessions. So as you can see here, we showing an example that in this particular case, we would say 22% of the samples would be good, 36 would be in the basic level, and then we would have 41% of the samples would be outside of the 167 milliseconds. So it's a good way to compare and benchmark across networks, across devices, and also across games and cloud stream providers as well. So that was input latency. So frame rate. So the frame rate basically provides a measure of the animation fluidity of the gameplay. So a smooth gaming experience would basically mean that we have a stable frame rate and we don't see a lot of variability. We don't see a lot of jumping between, we measure the frame rate each second. So we're mapping that out basically as 1 second samples. So as long as it stays around, if the game's rendered at 60 FPS, we want to see it stable at 60 FPS. We don't want to see it jumping up and down or dropping and staying at a lower level. So we again take all these samples and then we band them into these thresholds. And again, we're able to quickly look. In this example here, it's looking across devices where we can quickly see if one device is performing better than another device. In this case, the LG Stylo, we saw definitely a drop off in the frame rate. It wasn't able to maintain a 60 FPS, and in some cases, it was dropping below 20 FPS. All right, so that's frame rate. So let's now look at cloud gaming and ping as a proxy, because we've seen a lot of data that's available now where there's ping is being used to ping the game server or a reference server to try and estimate what the gaming input latency or the game experience would be. So just want to highlight here that from this example, this was playing Destiny 2 Stadia at 60 hertz, streamed at 60 hertz on Windows Chrome. We can see that there's a lot of elements that contribute to the latency. Even the peripheral latency could be, really high-end mouse could be 1 millisecond. If you play with a Bluetooth controller, you could see an average 30, in some cases even higher than 30. So what we're showing here is that network's important, but it's not the only thing you need to think about or to if you're doing a ping, you're measuring the network round trip time. So you could miss out on what's happening in these other elements, which are also contributing to the end-to-end latency. So for example, the frame packet buffer and the video decode could add 2 frames or up to 30 plus milliseconds into that end-to-end latency that we're measuring. And there's some latency also added from the display latency at the before as it's rendered, and you see it on the display. So overall, we see, with this example, we're seeing 85 milliseconds to 276 milliseconds that you could see based on, the configuration of the test, the device, what the network's doing. Okay, let's jump in now to this slide. So the other challenge with using ping to try and estimate what the round trip time or the end-to-end latency would be is that if you have a peering arrangement, so if one ISP or a mobile operator has a peering arrangement, the ping may not follow the same prioritized peering hops that the gaming packets would follow. So now you're pinging a server, but you're not really following the same route that the gaming packets are taking. So you're really not really capturing what the actual game experience would be. You're just pinging a server and you're getting some response back. So it's quite important that you have to be careful when you use ping as a proxy for trying to understand what the end-to-end gaming experience would be. The other thing we've done is we typically, and we'll show an example for the ISPs we benchmarked, we map the ping time against the input latency. So you can see just in this example that it's not linear, so it's very hard to say, well, because of this ping, I would see this overall input latency. So it is something that you have to be careful with when you're using ping as a proxy. So let's now jump into some data we collected.
Michael, we have a question from Octavio. I hope I have Octavio's name right. It's Octavio Yasmin, and we have a really interesting question. Octavio, can you unmute? Oh, there you are. Can you unmute and join the panel and ask the question? Welcome. There you are.
Hi, hello.
Hey.
Can you hear me?
Hi.
Welcome.
Yeah.
Welcome. We are analyzing about the protocols that we can use in order to see what is happening in our network in the latency in the gaming and other services that are latency sensitive. That is important for us to understand when we can use TWAMP in order to be sure that the network path or the latency in the network that is not about a misconfiguration in our routers or maybe in the CPE.
Okay.
And the question, and the question is, Octavio, I know TWAMP, but TWAMP or TWAMP, however it's called. What is the exact question, Octavio?
That is useful tools in order to reduce the latency or see which is the point of, the point in the network that is aggregating some latency. Maybe it's in the CPE, the buffer bloat, or maybe it's on a misconfiguration in the routers inside the core network.
Okay, I'll answer it from a game bench perspective. I guess one thing that we do, as I said, earlier on when we started the webinar, we look at everything from a gamer perspective. So what we do is when we when we're looking at measuring performance of cloud gaming, we are only looking at gamer metrics, and then we try and translate it to using, for instance, if I were to look at the input latency that we've been showing, we try and translate that into, let's say, round trip time. We try and understand of the input latency, if the input latency is 100 milliseconds, how much of that is the round trip time for the server and back, and how much of that is how much jitter is there in that, right? So we don't, but TWAMP you use only when, I guess, when you control the server and you're able to actually stream traffic to the device, right? In this case, because we're using real workloads, we don't rely on TWAMP or any other protocol such as that. So I know it's incredibly useful that once you've identified that there's a bottleneck in your server, to be able to, set some regressions, or, to be able to constantly monitor TWAMP or something like that is useful. But I think what we're trying to, come up with is actually, why don't you use the real game? Why don't you use the real service to actually benchmark the network and run the content, real content, over and over again? Because sometimes when you use, ping, or when you host your own server, you might be missing routing issues, you might be missing peering issues. There's a bunch of things that you can actually miss when you use other techniques, which are valid. I'm not saying it's not valid, but as a philosophy, what we try and do is to stick to measuring performance right from the gamer level.
Okay, thank you.
Yeah.
Thanks very much, Octavio. Ed Lambert, are you out there? We've got a question from you. Love you to join the panel and jump on in. Welcome.
Sure. Thank you. Can you hear me okay?
Yeah, absolutely.
Yes, sir.
Okay, great. Yeah, my question, and maybe I missed this, is I can see that you're showing kind of that combined latency of the device, the server, the network. Do you break that down in your reports and show which in your actually reporting and measurement, can you separate those elements, the network from the device, from the server?
I'll take a stab, Michael, add, okay?
Yeah, all right, go ahead. Go ahead.
So here, if you go back to the picture, typically what we measure is not, we don't measure the peripheral latency. Peripheral latency, Ed, is how much time it takes for the input to actually get delivered. We start from there. We start from when the event has been delivered, because it's a software solution. And then we go all the way down back to it being before it is held off to the display. So we have numbers. So we have, for instance, with Android, we have numbers, and for Windows, we have numbers. So if you're using Android, and if you're using, let's say, a Bluetooth controller, you have to add about 25 milliseconds.
Gotcha.
25 to 30 milliseconds for the peripheral controller. The software will not report peripheral controller. And we try and further break that down when we go into, we try and measure telemetry from the platform as well, Ed. Depending on, like, for instance, if and you're using Windows and using let's say the Chrome browser, we'd be able to extract what the service thinks is the round trip time from the logs, right? Because all of these services, like your Stadia or GeForce Now, they do also try and tell you have to know where to look. But once you know where to look, they tell you what the round trip time is. So now you've got the overall latency. You can get the round trip time from the logs. Then you can make an informed guess about what the game server latency is. So you have to do this process of elimination. We can't give out everything. We don't actually break down everything, but we do break down wherever possible, we try and break down the RTT, the jitter, and packet loss, the network metrics, as we call it. That's something we try and make available to whoever is using the tool.
Great. Thank you very much. That's perfect.
Yeah,
answer. Thank you.
just to add to that, Ed, the other thing, and I was going to cover that, as we go through the slides, but while we're playing the game, we're also pinging 3 IP addresses, the endpoint server. We're also pinging your router gateway, and we're pinging to reference Google server. So for that,
Okay.
we can tell you what your Wi-Fi latency is, or whatever however you're connected as you play, and you'll get that every second in the game while you're playing the game. And we do a net trace as well periodically in the game to show where the packets are being routed. So that gives you an idea. If you see an issue with the metrics, you could then go back and correlate with if you saw something, to your router, was there a delay to your router from the ping, or did you see some network issue? Say you're pinging the Google server and you saw that spike up, and that spike correlated with your ping to the game server. That would tell you then there's probably something happened on the network, either the ISP or the mobile network.
Got it. Thank you very much. That's that's awesome. Thanks.
All right.
Thanks so much, Ed. Really great questions, Octavio and Ed. Really appreciate it. Everyone else, please dive in. Oh, do we have yet another one from Zhao? Please, Adele, can we bring Zhao into the panel if you're comfortable joining? There you go. Welcome.
Hi, Sean.
Yes, I do have a very quick follow-up question, similar by aligning the logic that Ed asked before. When you segment out the latency for the round trip query, when you send the packets, then you observe the value which indicate the round trip time. But wouldn't that be just the combination of the network latency together with the game server latency when you just see the logs from WebRTC?
Let me try and understand. Zhao,
So,
can you measure? Sorry, I'm
so I guess my question is, how do you segment this network latency out when you see both the network?
So when it comes to
and game server latency.
Sure. So network latency is generally reported directly by the platform vendor. So they will report it as something like RTT in the logs. So if you, in case of Android, and let's say you're using Xbox native app, you'd be able to see a log that says every now and then, what was the round trip time average for that particular second. And now that is what Xbox is thinking is just the round trip time, right? So if you had, our software doesn't measure peripheral latency. If Xbox is saying that, let's say the round trip time is 30, out of, if our software is reporting, let's say 80 milliseconds, you take out 30 from the round trip time. So 50 milliseconds is for everything else, which means the cloud server's latency. How long did the cloud gaming server take for, how long does the cloud gaming server take for it to render that particular muzzle holding frame, the animation frame? How long does the decode take? All of that is clumped up into the 50. But round trip time usually is clearly mentioned, usually by the vendor. So we rely on the fact that the vendor will report things like round trip times. So it's just that now you can ask, how can you separate out the other metrics? It is hard. You have to, when it comes to the game server latency, you'd have to, we know that, for instance, Stadia is the best, PFN is the next best, and and what's that? Xbox usually is usually the performance is lower compared to them, and that is you'd have to find a game where you can keep all the variables constant, and you'll have to repeat these experiments on a device. But it's very hard to isolate everything. Some of these you can get from WebRTC, for instance, if you the what is called as jitter buffer delay, right? Jitter buffer delay is what basically the time between when the first packet for a frame comes till when the last packet, till when the frame is actually pulled out for decode, right? So there are certain aspects, certain things you can measure, and you can find out certain devices actually play a role. when it comes to actually decoding. So it's not a straightforward answer. For RTT, we just rely on logs, so to say. Michael, do you want to add?
Well, we have two approaches. We have the logs, plus we are actively pinging because when we play the game, we're sniffing the IP address. So we're doing some we're doing some PCAP capture. So while you're playing the game, we're looking to see which is the IP address that our UDP traffic is streaming to, and then we automatically pull that IP address. And then during the gameplay, we ping that IP address. So there's two sources. I think, Karthik mentioned that we can pull it from the telemetry, but we also can pull it, using our active approach as well.
Oh, I see. Yeah, just to rephrase a little bit. But previously you mentioned that because the game packets is different with ICMP packets, then the routing scheme or the priority might be different. Then from your experience when you do the pinging, do you see any significant difference comparing with just sending the ICMP packets versus sending the real UDP packets when you play the game session?
I think we're using UDP ping. I don't think it is in the in-game is a UDP ping. So we're not using ICMP. So we are, and we are comparing, that with the telemetry, and it correlates pretty closely from what we're seeing when we can pull telemetry RTT out.
Oh, so in other words, in your previous slides, when you show the dots of those correlation between the latency and a pin,
that was
a UDP pin instead of a ICMP pin.
Yeah. I think it was just, as even with a UDP ping, whether it's an ICMP or UDP, there's still smaller packets, and even if the routing's close, you still have things like packet loss, which you're not capturing in the ping, that could impact your input latency. You could drop frames. So there's lots of contributors that mean that we would see this type of effect. Yeah. So what we're trying to show here is just doing a ping alone, even if it's routed the same way, it is not necessarily going to give you a linear slope correlation. There's other factors that could impact your end-to-end latency that you're not capturing with a ping. Yeah. The processing delay, you may get processed by the game server in 1 frame. It may take 2 frames, it may take 3, which you're not going to see from the ping. Yeah.
Guys,
So,
we are going to need to jump on in order to keep time up. This is, I think, Zhao, it feels like a question that we might want to carry on after the webinar. And thank you, everyone, for your great questions. We have a little over 10 minutes left, and I just want to make sure that we can give Michael the opportunity to get to the end. So my apologies for jumping in there. Zhao, thank you for a great question. Very interesting discussion. Michael, roll on, please.
Yes, so we did some sample testing in the US. Remember, just to make this clear, this was limited testing. This wasn't conclusive, and we're not claiming here that one operator is better than the other or one platform is better than the other. But just to show, we just to explain, we had 2 ISP networks, Optimum in New York and Cox Cable in Orange County, just south of LA. We had a couple of testers, and we ran through multiple 15 to 30-minute gaming sessions to collect enough data to be able to generate some statistics. We played Destiny 2 on Stadia and GeForce Now. And we also played Destiny 2 natively on an Xbox console as well. We wanted to just show what the comparison was between the console experience to what current cloud streaming experience would be, just to highlight how cloud streaming is comparing with what a lot of gamers that have consoles are being used to as far as their responsiveness and their their experiences. So let me jump in. I know we're running out of time here. So just on this slide, we're just showing you the input latency against time. So for all the sessions combined for Cox Stadia, Optimum Stadia, and then the GeForce sessions. So we combine those sessions. You can see the variability we see from input latency across these. So that's interesting as a first pass, to look at these and say, hey, does it, can we see anything in the data? Can we see a step function, or could we see periods where, the medium or average latency was stable and then it jumped up or dropped down? So this just gives us the first sort of raw view. When we look at the statistics, we can see Stadia from a medium and average perspective was performing better than GeForce on the same networks. And also the spread of the samples was much better on Stadia than on GeForce for the limited samples that we have here, just like I said, just to bring that up again. And then when we compare these against the console, right, with the console, we use the high-speed camera that Karthik mentioned earlier, so we're pretty accurate readings. We can see we're looking here at 74 millisecond medium, whereas we saw the best was 112 on Optimum Stadia. So significant, difference between a console experience to a cloud stream. And then the 90th percentile, again, much tighter samples, input latency samples we got on the console. So, all right. Now, so that's the aggregated data, and like I said earlier, that gives us a first pass, but it really doesn't tell us, well, how do we then convert that to some kind of user experience rating and be able to benchmark again between networks, between platforms, and even between devices. So when we convert those samples now into a distribution and bin them, we can see that overall Optimum Stadia, in the limited cases we tested, would have shown as performing better from a user experience for input latency, because we saw 90% of the time we saw a good sample, so good input latency samples, whereas Cox Stadia we saw 82%, and we saw slightly higher poor samples as well while playing Stadia, Destiny 2 on Stadia on Cox. So this again is a easy visual to quickly compare between, benchmark between platforms, devices. And then when we compare that with the Xbox console, we see significantly better performance. We're seeing great performance on the console, which on any of the CloudStream sessions that we ran, we didn't see very many great samples, meaning less than 83 milliseconds. So this is a sort of good gold standard benchmark to, when people ask us, well, what should we be targeting? What should be the numbers? I would say this is a good start. If you can start getting console level latency performance when you play the game over CloudStream, then I think then you can start to, potentially start attracting console gamers over to play the game on your network over CloudStream. Okay. So jumping to GeForce Now, we saw very little difference between GeForce played on Cox versus Optimum. They were very, very similar as far as the user experience mapping. So again, slightly higher than Stadia. We saw slightly higher latency values when we played the game on GeForce compared to Stadia. But between the networks, it was a very similar experience. And remember, one was played in California, one was played in New York. So the routing would have been significantly different, but the overall experience was about the same. So now we jump into frame rate. So when we look at the frame rate performance, as we mentioned earlier, we capture the real world frame rate while playing the game, and we calculate the variability over the network. So this is the observed frame rate, not the sent frame rate by the game server. So we can see here pretty much very good performance across most of the sessions. We were close to 98 to 100% with most of the Optimum and Cox Stadia, Cox GeForce. Where we saw a drop off was an Optimum Stadium, where it wasn't able to sustain 60 FPS. It was dropping below 57 for 18% of the time. So that was definitely something that could, would be worth investigating further to understand why we were seeing frame drops, or there was potentially high jitter, meaning we didn't get the packets in time to generate or keep up with the 60 FPS. So let's jump. I know again we'll run out of time, so I'm rushing. This is how, when we map the round trip time against the medium input latency, we saw fairly good correlation for the Stadia sessions, not so much for the GeForce sessions, and we saw a bigger spread there. So overall, the correlation was moderate to poor. It wasn't a great, we couldn't look at these ping numbers and say, hey, we can estimate what we believe the input latency would be. So that was, based on, again, the limited samples. When we look at the actual, values, we can see that Cox Stadia and Optimum Stadia, we had lower ping, meaning less hops closer to the servers. And also, as I said earlier, we run a net trace every 5 seconds while playing the game. So we actually pull the whole path those packets are taking, likely taking when we play the game. And then we calculate the average number of hops. So you can say GeForce Now, we were seeing an average 8 hops, whereas for Stadia, we're seeing 4 to 5 hops. So definitely would have contributed, less, servers, less switches, the packets were going through. So it would have contributed to, the lower ping times that we saw. And also we pull out from the IP addresses, we pull out where those servers were. For Optimum GeForce, we saw it going to 2 distinct servers, one in Chicago, one in New York. So I'm going to turn over now to Michael. Or was there some questions, Michael, before we jump into?
Yeah, we have some questions. Everyone, of course, is getting very lively just as we're running out of time, which is great. So, guys, what we're doing, and we've already sent notes to some of you. If we don't have the time, which we don't now, to get into these questions, we are very, very happy. I can see Kay engaging with some of them in the chat now. We're very, very happy to pick up that conversation via email. So, if you feel comfortable, and please don't feel you have to, if you feel comfortable, just give us your email and we'll keep track of your question and we will respond by email. We are capturing all of this. So apologies. I think we've had such a good session that, as always, we end up running tight on the clock. But Michael, well done. In fact, well done both of you for a great session, and well done, Michael, coming in without galloping too much towards the end. So we're going to move towards wrapping up now, guys. Thank you so much. That brings us to the end. Thank you so much, everyone, for sitting in and for those excellent questions, which still continue to come. Special thanks to Kay and Michael for running a really great presentation, very clear, very educational. I think we've covered a huge amount of ground. And also, of course, as always, to the invaluable Adele Tibier, who's been running the session in the back office for us. I don't know what we'd do without her. The recording, some of you have asked about this, the recording of today's event, which of course includes the slides, along with our special labs report, which summarizes the performance analysis that Michael was just running through just now, will be shared with everyone shortly. And just so you know, we have some new seminars coming up in the next couple of months, just to give you a taste of what's coming up. We'll be focusing one on native gaming, so looking at metrics and data collected for popular online games like Apex Legends, Rocket League, and Valorant. We'll be looking, as we must occasionally, at mobile operators. Does 5G have a measurable impact on cloud gaming experience? Is a huge question right now for gamers, for operators, and of course, for game developers and publishers. And as always, we're always interested in going across the world with other geographies. So to continue this particular series focusing on gamer experience and network performance, we'll be looking in the future at European countries, possibly focusing Germany, France, and Asian countries, possibly looking, I think, at Korea and Japan particularly. So looking at the current state of gaming experience and network performance in those markets. So keep an eye on your inboxes for details of our next webinar. Thank you once again for being here, and we look forward enormously to seeing you again next time.